Good day, everyone. I'll be presenting this study with the title Simulation of a 32-bit Synchronous FIFO using Verilog and Xilinx ISE. First, let me share the introduction of this study. FIFO, or first in first out, is an approach to handling program work requests from the queues or stack so that the oldest request is handled first. In hardware, it is either an array of flaps or read-write memory that store data given from one clock domain and on request supplies with the same data to another clock domain following the first in first out logic. Basically, FIFO divided into two categories like synchronous and asynchronous. The objectives of this study is to use a FIFO buffer that will output up to 832 bits data input and automatically keep track of the order in which write data enters into the module and reads the data out in the same order. Specifically, the objective of this study is first to build a Verilog code that will show a 32-bit synchronous FIFO buffer. Secondly, to synthesize and display RTL schematic. And lastly, to build test bench that shows the Verilog codes if matches the desired output. Operation of FIFO with the 8 data values is shown in this diagram. The system has the capacity to input up to 8 data and output the entered data after reading. Here in this slide, truth table of control mechanism or operation have shown. Top level design of the FIFO buffer. The top level design of the 32-bit synchronous FIFO. In the black box, there are 6 data inputs. One of it is 32 bits, while the other data input signals are scalar. And also, at the right side of the black box shown, the 3 output signal. One of it is 32 bits, while the other 2 data output signals are scalar. On this slide, sample codes are shown for Verilog module and the variables of input and output signals. The code shown is just a part of the whole source code of the 32-bit synchronous FIFO buffer. Also shown in this slide is a sample of test bench. The code shown is just a part of the whole source code of the test bench and the 32-bit synchronous FIFO buffer. Next, the simulation of a 32-bit synchronous FIFO buffer is shown in this slide. Next is the result and discussion. In this section, the proponents managed to run simulations of the 6 test cases that was stated in Table 2. The Verilog modules are coded and integrated as one to demonstrate the goals of this research project. Test bench codes were also created to perform the different simulations through varying value of inputs. Clock value was firstly assigned with leading edge and trailing edge using values of 0 and 1 respectively. Simulator was used to show the output digital waves using the time scale of 1 US over 10 NS. For the conclusion, the researchers' proposed project was completely successful using Verilog HDL programs in Xilinx ISE and simulated in ISim Simulator. Verilog HDL was extremely helpful to the project's proponents in order to implement the programming part of the project. It delivers informative waveforms that are quite useful in understanding the study concept. As a result, the researchers concluded that the Xilinx ISE tool can be validated as a learnable simulation tool and a fantastic integrated development environment. It was also discovered that utilizing Xilinx ISE is easier to design, synthesize, and simulate various digital system circuits, but we only need to be extremely careful in programming, given that we are developing and implementing the synchronous FIFO buffer. All Verilog output waveforms simulated and shown by the Xilinx ISE tool will reveal that the simulation of a 32-bit synchronous FIFO buffer using Verilog in Xilinx ISE is successfully finished and feasible for the implementation. Here are the members of our team, the proponents, led by Jerico Vergara, and team members Pauline Adesa, Genaline Generoso, Sarah Angelica Rodillas, Maria Katrina Torreja.